Hello, and thank you for tuning in to episode 5 of the Exebenus podcast series, LivePulse. I am your host, Anne-Siv Uberg, Vice President Marketing and Commercialization for Exebenus. Our LivePulse series is all about digitalization and automation in oilfield operations. We've so far been talking about the merits of digitalized operational procedures, and we've highlighted the benefits of automatic tracking during execution. Today's episode turns to the topic of machine learning and features a conversation between Serafima Schaefer, Well Digitalization Manager, and Exebenus data scientist Tim Robinson. Over to you, Serafima and Tim.
Thank you for joining me, Tim.
Glad to be here.
This year, Exebenus has introduced 3 machine learning agents related to stockpipe, and we plan to get into the details of those agents in our next episode. But for today, Tim, I'm hoping you'll help us understand machine learning generally. Let's start with a really basic definition. What is machine learning? And what is the difference between machine learning and artificial intelligence?
They are closely related, but let me start by answering your question, what is artificial intelligence or AI? Basically, it's the use of mathematical algorithms to synthesize the capabilities of the human brain. I said they were related, and here's how. Machine learning is actually a subset of AI, in which that functionality is often applied to specific tasks that could be done by machines as well as humans, and in some cases better than humans. Machine learning algorithms enable systems to learn a task from data and to get better at doing it with experience, and importantly, without being explicitly programmed to do so. So we as data scientists develop computer programs that can access data and then use it to learn for themselves.
Sounds amazing. Can you break it down a little more for me? Are there different types of machine learning?
So we generally talk about 2 broad categories, and I'll park reinforcement learning aside for now. First, we have supervised learning. This is the most common type. You train a model to learn the relationship between a set of inputs, these are often called features, and a set of known outputs, which might be categorical labels or numerical values. So we're talking about tasks that involve recognizing patterns, classifying information, forecasting, that kind of thing. Secondly, we have unsupervised learning. Here, you're letting a program explore data to discover interesting patterns, groups, or clusters for you. Both of these categories are used across several industries, including our own.
Could you share some examples that we may be familiar with?
You don't have to look any further than your smartphone, actually. Do you unlock your phone with your face? Or use autocorrect functions for texting? That's machine learning.
Okay. So I'm using it all the time. So Google Translate would be another example?
For sure. And so are those image tools that aid you, or transfer the style of one image to another. These are all using machine learning.
What's the latest hype on the scene, Tim?
A good example would probably be generative language models like GPT-3 from OpenAI. This can generate realistic text that's often quite hard to distinguish from text written by humans. This has a lot of potential for improving virtual assistants such as Alexa and chatbots, for example.
Oh, yeah, that's pretty advanced. It's really popping up everywhere, isn't it? Machine learning is such a powerful tool, but your average engineer probably hasn't had much exposure to it yet. Well, apart from on their mobiles or online. Or am I mistaken?
Actually, there are quite a few places where machine learning is used in our industry. Let's explore. Some of the well-known applications are in image processing or computer vision. We can use this for analyzing borehole images, for example. The industry produces a huge amount of reports. Written reports, we should clarify. Language processing, normally used for speech recognition, translation, synthesis. This has been applied to extracting data from these reports, but this is still in the early phases. Forecasting is used in many ways, such as forecasting sales. In our industry, it's used for sales forecasting by the operators' trading departments. An example of unsupervised machine learning often used in other industries is customer segmentation. But in our industry, companies are exploring its use in the geophysical domains.
Well, that's not bad.
Not at all. I'd say machine learning is also entering the real-time operations space, specifically to do 2 things, to predict and to optimize. If we look at the predictive uses, they are often about detecting anomalies early and then avoiding hazards.
That's exactly where we are deploying machine learning in Exebenus. Our stackpipe agents, which are systems containing models, predict situations where stackpipe is likely to occur and provide alerts to the real-time operator center and the crew in time for them to act.
Correct. And another example is well control, using machine learning to provide early detection of gains and losses before a kick or a blowout can occur. These are uses where machine learning is improving safety and, of course, also reducing operational costs.
So I'd like to understand more about what I need to make machine learning work. Tim, you mentioned earlier in our podcast, machine learning models need historical data to be trained. Well, the things that tends to concern our clients are, do I have the data to use this technology? And do I have enough to make it work or train it?
Sure. Well, first and foremost, you need the right data for your problem.
What do you mean by that?
Quantity of data is not always the main issue. You need data that is representative of what you are trying to build a model for. For example, if I want to model downhole circulation densities at high pressures and high temperatures, I wouldn't expect good results if I built a model based on data from shallow, low temperature, low pressure situations, and then tried to apply it to HPHT.
And that brings up another common issue. We have loads of historical data and real-time data available, but they may be from different fields, regions, or different basins.
That is okay, but it means the data may contain some uncontrolled variables, such as different techniques used by the operators, different operators for that matter, geological features, or different equipment. Some of these things may limit the data's applicability in other regions and present a challenge for machine learning models to generalize. This is why it's important to carefully validate models on situations they were not exposed to during the training process, and to understand the uncertainties involved.
So it's not enough to have a large quantity of data. I need to be careful on how I curate my data.
For generalization, it's better to have a reasonable volume of data from a range of diverse wells than to have a huge quantity of data from just a few wells in one area. The point is to be careful with the dataset you use. Is the data you have descriptive of the problem you need to solve? Is it representative of the underlying processes that you're trying to model? Let's use an example of demographics. Let's put on our statistician hats for a minute and imagine we're trying to understand if males or females are typically taller. We have a hypothesis that males are on average taller, and we measure the heights of 500 males and 500 females as our sample groups. But if we only considered males under the age of 10 and allow adult females, then we would conclude the hypothesis is wrong based on our data. Our model for male-female heights would not generalize because our data was not representative. This is sampling bias.
Clearly, before you know whether or not you have the right data, you need to know what the problem is that you want to solve. And more so, it has to be data that you know and data that you have always have available, particularly for real-time applications.
Correct. You need a well-defined problem. We could build a highly complex model that is less task-specific and try and apply it. But that may not be the most successful approach. You should start with the problem and then build the model. Third requirement, therefore, is domain expertise. The better insight you can apply to how the discipline works, the more successful your machine learning model will likely be. The best results will come from combining domain expertise with machine learning expertise.
In episode 4, we discussed how digitalizing procedures enables recognition and validation of activities such as drilling, tripping, connection, sliding, and so on. In machine learning, we connect the activities to the model. This helps provide them with context and improve performance. Let me give you a non-oil gas example. A red object will look different to you as a driver in the rain, in the darkness, or in the fog. If this was a self-driving car using machine learning algorithms, we would provide the algorithms with information saying we are driving in the rain. Team, when we talk about defining the problem, it makes me wonder about where generally I should apply machine learning.
The short answer is machine learning can solve problems that require a lot of time and effort.
I take it there are many types of applications.
Yeah, different types solve different problems. Let's start with a type where your data contains the answer completely, but you might need to automate a high volume of work. So let's go back to supervised machine learning, which I mentioned earlier. You could be asking the program to sort data into categories using information that may be obvious to humans. Good example is image processing. If you want to classify pictures of cats and dogs, as a human, you know the difference between these pictures of cats and dogs. It's very normally obvious within an image. The model needs to adequately use that information, which is typically hard with conventional models.
What about hyenas? Biologically, they're cats, but they look like dogs. I guess convergent evolution is no friend of machine learning.
Great point. You would need additional information outside of the general visual patterns in the image to be able to make this distinction.
Another type, I guess, is you have the data and the answer is buried in this data, but the sheer volume of predictions required is so great that it is beyond the capability of humans to process. This has some overlap with the previous example.
Yeah, and the third type is where the data contains too many variables for a human to easily make sense of. Good example of this is credit scoring. There are many factors to take into consideration when deciding if someone is creditworthy. A human might be able to assess individual variables, or maybe even small groups, but it would take a long time, and a human is likely not going to be able to use all of the information adequately in a consistent way, or to capture all possible combinations and kind of coalitions of variables. Anyway, I'd add a fourth category here. Situations in which you have data and guess that there is some kind of relationship, but you're not quite sure what it is. And you can use machine learning to inform yourself here. For example, you want to understand some groupings which might exist within a retail consumer base. Maybe the buying patterns present among certain demographics-based groupings to inform a marketing strategy. What you're doing is asking an unsupervised machine learning model combined with some interpretability tools to discover that relationship. You'll need to provide some framework, which is what we mean by the model, but not impose too many constraints.
Most of us in the drilling and wells domain are used to using and understand physical models for different processes. They've been refined over many years, and they work. What's the argument for switching to machine learning?
Yeah, I mean, by all means, if a conventional physical model is faster, more accurate or more effective, and also the input variables are consistently available, then you should use it. The key point is that it works. We don't model the motion of a ball falling in a vacuum using neural networks. We have Newtonian physics for this. However, a physical drilling model, I should say, is intrinsically imperfect because it requires a large amount of variables and insight into how the model works, and entails a simplification of what you're trying to understand. The more terms that are involved in describing a problem, normally the more assumptions and approximations you're required to make in creating or using the model. These are still powerful tools though. We just need to understand the limits to their applicability. Machine learning models, on the other hand, are statistical models. So if you don't have a physical model, or if maybe some key inputs of physical models are not available, then machine learning can help you exploit these interesting relationships without needing to explicitly define them. Using supervised learning as an example, we can consistently take available variables from the well site and use a statistical model to infer how these approximately relate to some variable of interest, such as estimating downhole ECD based on surface parameters. Even with black box machine learning models, there is a branch of machine learning dedicated to explainability, which can help us interpret these.
What about some of the other capabilities that have been used in the industry? In our last episode, Anasif and I talked about simulation modeling and digital twins. Is there an argument to be made for using machine learning rather than these other options?
I don't think it helps to think of it as an either-or choice. Machine learning is not here to replace other forms of modeling, but rather to augment and complement what we're already doing. You might have physical models and machine learning models feeding into digital twin simulations. These are not necessarily competing technologies though. How you apply them, how you balance them, it really depends on what the problem is that you're trying to solve.
I guess the bottom line is, with lower oil prices and higher lifting costs, company needs to produce more at lower cost, and machine learning can help achieve that.
Yes, machine learning can help achieve that for much less investment than if you had to add more equipment, rigs, or people into the equation. And as we described, machine learning can be powerful as a predictive hazard prevention tool. So it's ultimately helping to increase productivity, safety, and reduce costs.
Speaking of people, the industry has lost a lot of experienced people over the past 10 or so years, so we have fewer people carrying a much heavier workload. I can see why there's growing interest in adopting machine learning tools to help everyone be more effective. But how easy is it to use machine learning tools?
Our stuck pipe early warning tools are cloud-based and can be directly integrated into monitoring tools that a company is already using, such as Kongsberg's Sitecom Discovery in the Real-Time Operations Center.
Well, Tim, this has really helped to sort out the larger world of machine learning. We've mentioned that Exebenus has developed machine learning agents that signal 3 common high-risk conditions that typically result in stuck pipe issues, namely differential pressure, hole cleaning conditions, and wellbore geometry. Team, I hope you will join us for episode 6 of LivePulse and help us to take a closer look at how our machine learning agents work.
Alexa, add a LivePulse episode 6 recording session to my calendar, please.
Yeah, as always, we welcome comments and questions for our listeners. Use the links on the Exebenus website, on our YouTube channel, or on Spotify, and watch those sites for our next episode of LivePulse. Please share the podcast with your friends and colleagues. Bye for now.